This video is going to look at how we change the rotation of an object. If it's rotating some way and we want it to stop, or we want to make it start rotating, we're going to be talking about torque here. So changes in angular velocity are caused by torque. That's the definition for torque. It's what can cause changes in angular velocity. And sometimes you'll see it called turning force. Sorry, I blanked on the term for a second. So it's the force that can kind of make things turn, if you want to think about it that way. The variable for torque is the Greek letter tau. You can look that up if you want to see kind of a typeface version of it. And the equation for torque is going to be tau is equal to r times F perpendicular. So this is the radius, or the distance between the pivot and the location force is applied. And F perpendicular is the perpendicular component of the force. So I do want to talk about this a bit, and I'll kind of clarify this a bit later. Don't worry too much about the perpendicular component and how to calculate that and stuff like that. The main thing we want to talk about is if you're pushing perpendicular. So if I have my, let me grab this. So I've got my pen here. Should be able to see that hopefully. If this is my pivot where my right hand is, which is, over here, and I'm going to push over here, the radius would be this distance from here to here. And then the whole point of perpendicular is if I push perpendicular, then I can just take that force and multiply by the distance, and that gives the torque. But if I push at some angle, then I only get a smaller amount because only some of that force is pointed downwards. The rest is pointed inwards, and that doesn't do anything to turn it. So that's the main thing I want you to think taking away here is the more perpendicular the force is, the better it is for causing something to turn. And for our calculations, we'll always just calculate for perpendicular forces. But you should be able to qualitatively, like in broad strokes or kind of descriptively, talk about how, oh, if this one's at a more shallow angle, then it's not going to have as much of an effect as the same force at a steeper angle. So that's the main concern there. If that's not clear, or if you want to ask some questions, please check with me in class. R is sometimes called the lever arm. So if you see that term, that's our R here. The units for torque, you can kind of guess here. You've got a meters and you've got newtons. So it's going to be Newton meters. But however, unlike the Newton meters that we see in work, these do not equal joules. So if you remember, work was equal to R times force parallel. Torque is equal to R times force perpendicular. So a parallel force causes something to speed up or slow down. It does work. It adds or removes energy. A torque just causes something to spin or not spin. And I guess technically these do kind of equal joules, but in a roundabout way. But as far as we're talking about here, we're just going to talk about them as Newton meters, and we're not going to worry about kind of those weird situations. So, as I kind of mentioned earlier, we can increase the torque by increasing the lever arm, R. So if I apply a force farther away, I can give more torque. We can direct the force more perpendicular. To the lever arm. So the more perpendicular you're pushing, the better you're going to, the more torque you're able to exert. And finally, we can increase the amount of force applied. So again, this is something that we're broadly just looking at it qualitatively, like can we describe how I could increase or decrease, or if I say compare these two, which one's going to have more torque? That's what we really want to have a sense of here. Multiple torques can be combined into a single net torque. So if I have, a torque that's causing it to spin clockwise, another one causing it to spin counterclockwise, then we'd subtract or add those accordingly. And that's the idea here. So the overall net torque describes whether that object is going to spin and in which direction. So if I have a torque that's, 5 newtons clockwise and 5 newton meters, clockwise, and one that's 10 Newton meters counterclockwise or anti-clockwise if you prefer, we have a net torque of 10 counterclockwise. So overall this object is going to start spinning counterclockwise. And that's what we're really looking at here, is just kind of figuring out which way is it going to spin and how those combine together. There is a mathematical way to define the direction of the torque, but it gets into some vector work that we're not going to worry about for this class. And we're going to deal with some pretty simple examples. So we're just going to look and kind of intuit or reason out which way something's going to spin. So for example, if I have a seesaw or a teeter-totter, right, or a balance if you prefer, if I have an object sitting on this side and an object sitting on this side, A, and object B, we can figure out that A is going to push down on the seesaw on the left side, and that's going to cause it to spin, that's counterclockwise. So this, we'd say A is causing a counterclockwise torque, whereas B is going to kind of spin it this way, is causing a clockwise torque. So we're just going to kind of do that reasoning. Likewise, if you had a little person here that was pulling up on the seesaw on this side, that would also be a clockwise torque, because you can kind of imagine how this would end up spinning. Let me know if you have questions, but otherwise we'll leave that here with torque.